All right, so now we're going to look at nuclear chemistry. And so, what is nuclear chemistry? Well, it is a division of chemistry concerned with changes in the nucleus of atoms. And so, specifically, as we talk about the nucleus, we're really going to be concerned with neutrons and protons and how those change in chemical processes. So, just as a quick word of advice, when we talk about the formation of ions, so let's say Mg becoming Mg2 plus, this is a change in the electron shells or in the number of electrons, and this would not be a section nuclear chemistry because the change is not happening in the nucleus. So to start, let's just mention that some atoms exist in only one form. So an example would be fluorine-19. There aren't any isotopes or different atoms of fluorine that have different atomic masses. Basically, all of the fluorine you're going to see is fluorine-19. But for other atoms, you can have isotopes. And isotopes are just going to be the same elements that's lost or gained a neutron. So an element that has lost or gained a neutron. But they have the same number of protons. So an example of that, of course, would be hydrogen 1, which is just hydrogen, and then deuterium, which is still going to be the element hydrogen. Now it is just an isotope. So representing it with a D is what some people tend to do, but for clarity's sake, I'm going to keep it as an H, just so we're all on the same page here. So, some elements exist in one form, some have isotopes, and then a category of isotopes would be stable isotopes. So, stable isotopes are just forms of an element that differ in the number of neutrons, but do not decay. The change in neutrons don't affect the actual element enough that they are going to try to change the number of neutrons or protons. We'll get more into that in 1 second. But going on now, we have radioisotopes. And so all radioisotopes they are the different, or they are the opposite of stable isotopes. They are going to be isotopes that do decay. So they are unstable isotopes. Give me 1 sec while I just make that a little bit more legible. All right, so these isotopes are not happy with their neutron composition and spontaneously undergo radioactive decay to try to return to a stable form. So while, let's say, we have an example of carbon here, let's talk about a stable isotope first. So chlorine 37 and chlorine 35 are considered isotopes of each other. They are both still chlorine, they have the same number of protons, but now they have a different atomic mass. And that is due to a change in the number of neutrons. So, as we talk about chlorine 37 and chlorine 35, both of these elements are stable. They don't undergo radioactive decay. But that can't be said for carbon 12 and carbon 14. Carbon 14 is unstable and will try to undergo radioactive decay to change the number of neutrons or protons. And so what do I mean by neutrons, protons, and why am I talking about the ratio of the two? Well, if you remember all of the different, what's the correct term? Nuclear notation of an element. A is the atomic mass, Z is the atomic number, and then X is the identity of the element. For Z is just the number of protons. And A is the number of protons plus neutrons. So different elements like to have a different ratio of protons to neutrons. Small elements, so elements that are that have a proton number less than 20, typically like to have a 1-to-1 ratio of protons and neutrons. And you can see examples of that with, let's say, oxygen 16. It has 8 protons, 8 neutrons. Nitrogen 14, the most common form, 7 protons, 7 neutrons. Carbon 12, 6, helium 4, 2. You get the point. All of these have a 1-to-1 ratio, and their Z number, their atomic number, is all less than 20. But something changes when we get above 20. So for above 20, I'll actually just take this and move it a little bit higher up. So for elements that have a number of 20 or above and below 83, this is what we call, or these are what we call the heavy elements. And they actually have a nucleus that has a large number of protons. And those large numbers of protons are all going to be experiencing some proton-proton repulsion. They're all the same charge, so they're trying to get away from each other. And as a result of having that many densely packed protons, we are going to want to have a larger number of neutrons to kind of give us some buffer space between all of those protons. So instead of liking a 1-to-1 ratio, heavy elements prefer a 1 to 1.5 ratio. So let's say, for an example, we are talking about, well, heavy elements. Let's just look at the periodic table real fast. So arsenic 33, or arsenic 74, does not actually have a 1-to-1 ratio. It's a heavy element. So arsenic does not actually have a 1-to-1 ratio. It's a little bit off. You have 33 protons for 41 neutrons, and so that's a little bit closer to that 1.5 ratio. So now that we talked about that, let's talk about how these elements get to a more stable form if they are radioactive. If I have the wrong ratio of protons to neutrons, these elements, or these radioisotopes, have a way of dealing with that. And so we have a number of different types of radiation. So what you should know are the general symbols and then how they are portrayed. So beta radiation. Typically, you are shown this as 0 with a -1, and then an electron, or you could also see this as the beta symbol. A positron is just it's basically a positive electron. Positrons have the same mass as an electron, but they have a positive charge. So they'll have basically the same representation, except now we have a positive one. And for alpha particles are just helium. So it is just a little conglomerate of 2 neutrons, 2 protons, which will be helium. So why am I changing color? For 2, He, a proton has the symbol So protons have this symbol, and with a notation of, usually they just show a hydrogen, or you might see a P. Neutrons have the symbol 1, 0, and then the letter N. And gamma is always that strange one. You usually either see it in one of these two forms. Some form like that, of course, I'm not going to be able to draw it perfectly. Now, how are they portrayed? This is also important to know. Well, for a beta particle, a beta minus particle, it is just an electron. So we'll just represent that with a red color. And let's just say, whoops, of course. There is our negative electron. Now we'll look at our positron. It is just the electron, but with a positive charge. I'm not going to try to align those. Helium. Actually, let's use green for protons. So helium has 2 protons, 2 neutrons. Neutrons will be gray. Should probably make a list of all of these. So positive, positive. I'll just make a list real fast. Neutron, proton, and then kind of an electron, just because positrons, not exactly electrons here. So, moving on. A proton is just a single positive. A neutron is just a single neutron represented in gray. And then gamma is really just energy here. So for that, we'll just have the symbol of, let's say, energy or a photon, and then we'll have the gamma symbol. Great. So as we now get into the different types of radiation and what they actually look like, let's just give a helpful tip or two. So for dealing with the different types of decay, and you're trying to figure out the products of beta decay, alpha decay, and all of that, you should just know this. The mass numbers let's just say will. Mass numbers will be equivalent The mass numbers will be equivalent for products and reactants. And what else will be true for the products and reactants? The atomic numbers must be equivalent. And when we say equivalent, the sum of the atomic numbers on both the reactants and product side must equal the same number. So, whoops. Should probably just change that to atomic mass. Cool. So now we get into the fun stuff, beta decay. There are two types of beta decay. We have beta negative and beta positive. So for beta positive, this is also called positron emission. And what is going to happen is we are going to lose a proton and gain a neutron. That is the brief overview. As a result, our mass number does not change. Our atomic mass number is made up of protons and neutrons. If we lose one proton and we gain a neutron, we're just going to cancel out and have the same exact mass number that we had when we started. So the mass number doesn't change. But what does change? The atomic number. The atomic number decreases by 1 because we lost a proton. And so here I would just have, this is going to be a very colorful section here. So here we have a positron. So we have that positively charged electrons, let's just say that, positively charged electron. No use in dancing around the different words. So for this, we have 10, 6, carbon, so carbon 10. And what did it do? Well, it lost a proton, gained a neutron, and in the process of losing that proton and gaining a neutron, we also released a electron, or a positron, sorry. So, I'm really going to mix those words up. So, now we have boron 10, and we'll just say plus a positron. So that is positron emission, or beta plus decay. Now, beta negative. All right, so now let's look at beta negative. Now, beta negative is going to have an interesting process happen. We are going to lose a neutron and a proton is gained. So, in the process of this though, we don't just have a neutron that is going to react and then a proton is formed. We are also going to release a high energy electron. So, here's that electron. And the process, while it doesn't necessarily happen this way, it can be helpful to think about this. A neutron is going to split and form two different things. It's going to split and form that electron, and then also it's going to split and form a proton. And it just kind of helps me remember it because I have a neutral molecule, and if it breaks into charged molecules, I'm going to break into a positive and a negative. So that's what's really happening in beta negative. That neutron is now splitting into a electron and a proton. Now, before we just move on, just to kind of talk about these two beta emissions, let's just ask this or answer this. Why are they good for radiation? Remember, just going back as a quick review, we are trying to decay to get to a more stable proton-neutron ratio. So these elements that we're dealing with, carbon, boron, carbon, nitrogen, are all looking for a 1-to-1 proton-neutron ratio. So beta positive is losing a proton and gaining a neutron. So for an atom like carbon 10, we have, and let's just represent this with a few dots here. Spoiler alert, this is not how a nucleus looks. Here we have 6 protons and 4 neutrons in carbon, but we want a 1-to-1 ratio. So what's the best way to do that? Well, beta positive is going to take a proton and replace it with a neutron. So if I take one of these dots, one of these protons here, and I change it, now I have a 5-to-5 proton to neutron ratio, or a 1-to-1 ratio. So great. Beta positive is great when I'm talking about elements that have too many protons. Now, what happens in the opposite case when I have too little protons? Well, in this case, drawing the elements again, carbon 14, 6 protons, and 8 neutrons. So now for beta negative, the nucleus loses a neutron and a proton is gained. Great. So I can now take one of these neutrons, replace it with a proton, and now I have again a 7-to-7 ratio. And so what actually happened? Well, we have the same number of particles in the nucleus, both cases. So mass number does not change, and the atomic number now increases by 1.